Continuing on the topic of test design is a design technique known as equivalence partitioning or equivalence classes. And people who study test design find this a very good starting point when you have identified a variable and you wish to choose values to test. Keep in mind that in software testing, it's almost impossible to come anywhere near close to testing all the possible values of combinations of variables. So what people like to do is instead partition the values, take the values and partition them, put them into subsets. And each partition is suggested so that if we test any member of the partition, we would learn pretty much the same information, or we'd gain the same knowledge as for some other partitions. So the idea would be, if you have a variable that's important to test, take the possible values that that variable can have and partition them into different sets. And then once you've got these sets, you can pick a representative sample from each set to exercise the application. This is equivalence classes. So an equivalence class is really defined to be a subset of all possible test values of a variable. So this is a variable can have many values, so you take a subset of them, and we call that a class. Each member of the class, the hypothesis is that it will provide the same information to us. And if indeed it is a true class, it will teach us the same thing about the application, or about the treatment of the variable in the application. Each variable may have many classes. There's many subsets of values. The classes do not have to be mutually exclusive. They can overlap. Indeed, in some cases, it's almost considered a good idea that they overlap. So the purpose of this, the purpose of identifying equivalence classes, is to focus your testing. So once you've identified a class, you don't have to test every member of the class. The idea is you'll choose a small sample of the members of the class. I like to choose a few, depends on, I guess, what I'm testing. But some practitioners of testing argue that you really only need to have one representative sample from an equivalence class. So you take a small number of members of the class, a small subset, and you basically focus the testing. This reduces the number of test cases needed to learn the same type of stuff about the system under test. So we're just trying to reduce the number of test cases. Now, visually, you could look at this as using like a Venn diagram. So if you look at the possible values are A, and if you take the Venn diagram on the left here, B and C are partitions or classes, and they overlap. So you could probably choose a value that is in B and C at the same time, and probably one value from that intersection will teach you the most. If you only had one test to do, that's probably the best one to do. Or if you had this set of classes here, where we have A is all the possible values, B, C, and D are the subsets of them, they're overlapping, and you can see here that there's probably values here in the intersection of B, C, and D. Right over here, a value there would probably teach you an awful lot about the application under test, because you'd be touching, with one test, you'd be touching three classes. It's also possible that classes are all over the map. If you look at the diagram on the right here, you have basically the class B is way on its own somewhere, doesn't overlap anything. F is fully enclosed in C. So there's all sorts of ways that these classes can interact. And drawing Venn diagrams does show you the relationship between classes, but it's not really a very constructive tool to create classes. It's sort of if you can draw a Venn diagram, you could probably prove some stuff about classes mathematically, but practically speaking, this is really more just a teaching aid here. So really what we try to do is learn about equivalence classes by studying how the variable will be used in the software project, and we get sources of information from different places. One of the most popular sources of information about variables is the source of information about the requirements. You learn about the business logic and capabilities, ranges of values, constraints applied to the variable. You can also then look at code. Not all variables, but many variables are actually code programming variables, or relate to programming variables, or relate to logic around programming variables. So we can look at the code, look at decisions about the variable, or computations about the variable. And then we can also look at, for example, data structures, internal data structures in the code, fields and records and schemas in databases, and how things are entered. So we have all sorts of different sources of information. You can look at the code, talk about the requirements, talk to subject matter experts, gain insights into the variable. I like to suggest that there's three perspectives that I use when I look for equivalence classes. And I just call this the model I use, an AIM model. I build usually a mind map to represent this, but you don't have to. You can just make a list of variables. I look for variables based on A, application logic. That would be business rules. That would be restrictions, constraints, conditions. And the rules that we're looking for, or the application logic that we're studying, could be written down, or it could be implied. I may have to interview a lot of people to learn what they are. So those are the what I call A classes, application logic classes. Then I look at how data gets there. How did the data get into that variable? Is it entered? Is it calculated? Is it read from a file? Is it transferred by a message? And that's what I call the input classes. So input classes are based on how the data got there. So that they're not based on analyzing the business logic, they're analyzing the input method, if you will. So if I'm typing in data, did I type in a number or a string? Was it a pull down list? Did I choose a member of a list? All of this type of thing. Those are input methods. If I read a file, it's the contents of the file. So A is the application logic. I is the input method. And then the third place I look for equivalence classes is based on what I call memory, how the variable will be actually processed or represented in computer memory, in program memory, in variables, in data structures, or in database records. So I'm looking at how things are stored in memory. And that will also give me some ideas about classes, if it's stored in a byte or a word or a funny structure or a funny field definition or a string. So this is what I call the AIM model for looking for equivalence classes. So I start, look at the business logic, look at the input method, look at how things are processed and stored in memory. I do not always have information about the M classes because sometimes I don't have access to the code or the programmers who wrote the code that I'm testing or the architects, that type of information. So if in that case, if I don't have access to that information, I would be looking at the A and the I classes. I classes, almost always I have information about them because there's some sort of input method. A classes, I can always get some information because there's always some sort of business logic, domain logic, application logic. Let's take a look at how the equivalence classes can be discovered for an example function here. So imagine that we're testing a web application and we're trying to confirm that the computations are correct. The application is designed to compute a square root. It's, for the purpose of this exercise, let's say it's going to do the real square roots of rational numbers. So it's not going to be using complex numbers for the purpose of this exercise. Now let's say it's a web form. A human being, a operator, will type in a number and with their fingers type in a number and hit submit. And on the screen, we're supposed to get the result. What is the square root of the number that was typed in? So a user might type in, I don't know, 36, and 36 is equal to 6 times 6. So the square root of 36, if they type 36 and hit submit, they should get, or they expect to get, a 6 as the result. Now, when we look at this function, it's quite a simple function, but there's a little bit of complexity in the math behind computing a square root from the point of view of computational analysis. So what I would do first of all is to start to study how a square root is calculated. I would talk to a mathematician, someone from the math department, or someone studying computational methods or algorithms dealing with computational methods in mathematics. Maybe someone in computer science might be able to help us. And I would say, okay, let's talk to you about the domain. The domain is the square root. How would you say x can be handled differently in computing a square root. So if the variable in question is x, what the user types in, and we're trying to compute the square root of x, from the point of view of the domain, computational mathematics, how would you calculate the square root given different values of x? Really, that's the question. And the mathematician probably would suggest things like this at the beginning. They would say, well, it's pretty obvious. I mean, you're an engineer, you should know this, that at the very least, x is going to be positive, negative, or zero. And if it's negative, well, it doesn't have a real value. If it's zero, well, that's sort of the identity case. The square root of zero is zero. If it's greater than zero, well, then there's a way to compute the square root. We have algorithms to compute the square root for real numbers that are greater than zero. And those algorithms vary a little bit. So we have computational methods that are really cool and slick that work if the number, for example, is a whole number, or like an integer, a whole number. There's some cool ways to compute square root. And if it's got a fractional part, there's some other different ways, different methods to compute square root. All right, so I'm not suggesting I know the optimal way to compute a square root here, but the mathematician suggests, well, if the number is a perfect square, we have some ways to do it really zippy. If it's a prime number, we have other techniques. And if it's another number, we have other techniques. So they're suggesting if it's a whole number, it could be a perfect square, a prime, or something else. And those are different categories of classification of calculations that they're going to do. Now, I don't know what the calculation is, what the method is. I'm just learning these are differences. So, okay, so fine. So x could be greater than zero. It could be a whole number or have a fractional part. And if it's a whole number, it could be a perfect square. It could be a prime number or something else. So that's fine. Whole, fractional part, whole number, perfect square, prime, otherwise. If it's zero or less than zero, there's no further partitioning. So I guess less than zero in our case would be like an error condition, and equal to zero would be just equal to zero. So that's the identity case. So that's a breakdown of the A classes. Now, if I was to test then just based on the A classes, I would look at the end nodes of my mind map there. So I would say, okay, I would have one test, which is a perfect square, one test, which is a prime number, one test, which is a whole number, which is not a perfect square or a prime, one test for a number with a fractional part, one test with zero, and one test for a value less than zero. And that would be giving me coverage of at least one test case for each of the equivalence classes identified. And you'll see we got a rich variety in the types of data that we're exploring, the types of data we're testing. So frankly, when I'm testing, I try to do a random sample that's a bit bigger than one. But for day-by-day testing, that a lot of people start by choosing one member of each class. So the A classes are based on the application logic. We learn about them from requirements or from domain experts, people who know the subject matter. We learn about that. We partition the variable based on that. So in this case, for the square root, we identify 1, 2, 3, 4, 5, 6. We identify 6 different classes. The class x equals 0 is of course the identity class, and less than 0 is some sort of error condition. But those are all based on the application logic. Now, if we dive into the implementation, surely someone has to type in that number. So the number that they're entering is really a string that's being typed into a form on an application. So we have a form, a web form, and they're typing in a number. We're supposed to type in a number, but in fact, they're typing in a string. And when you're typing in a string, it certainly can be categorized as being a numeric or non-numeric string. And so we say, okay, if it's non-numeric string, then that should lead to some sort of error condition. We can't really say what that computes to in terms of square root. It's a string. It's not a number. And if it's numeric, well, it's quite possible that someone has typed in a number, but it's in a syntax that we don't understand. For example, you might have used a comma as a thousand separator, or a comma as a decimal separator, or some other notation. So there's numeric notations, there's numeric syntax, if you will. So there's valid or invalid syntax. Now for non-numeric, many of you might think, well, okay, there's a lot of different ways you can have non-numeric stuff, and there are. Usually for web applications, we look a little beyond just non-numeric, and we say, okay, well, maybe it's alphabetic strings, maybe it's control character strings, maybe it's binary objects, binary large objects, maybe it's other things like SQL hacks. So there's a whole bunch of things you can partition to break down non-numeric further. I spent a lot of time in multilingual computing, and I gained a lot of traction for testing non-numeric alpha classes given different codings of language. So you have multi-byte codings, Latin-based codings, right-to-left languages, and left-to-right non-Latin languages. So a left-to-right non-Latin language might be something like Greek or Cyrillic. A right-to-left language might be something like Arabic, Farsi, Hebrew, Urdu, Pashto, those type of things. A Latin-based language, French, Italian, Spanish, that type of stuff. And multi-byte would be languages that require codings which require more than one byte in like the Unicode code set. For example, it's pretty common for Asian languages like Chinese and Japanese to be coded in multi-bytes. So these are just examples of partitioning non-numeric. We can break that down any way we like. It's our choice how far we break it down. You could just leave it at non-numeric, in which case you say take an arbitrary non-numeric value and try it, or you could break it down to the types of non-numeric. It's a question of how much you want to dive into this analysis. Of course, you can go deeper and deeper and deeper depending on your partitioning. And then, so that's the I classes. So in this case, if we identify the non-numeric classes that I've selected here, and we're adding additional classes or additional tests to the ones we've already done in the A classes, well, we would need to add a test, I guess, for numeric invalid syntax. So something that's in a syntax we don't understand, like, for example, a comma for the decimal point might be a syntax we don't support. And then for the numeric valid, we don't really have to add a test because all of the tests we did for the A classes were valid numeric syntax, so we don't have to do an additional one. And then we have the non-numeric ones with alpha, with the 4 codings. There's 1, 2, 3, 4 there. The control 1, 5, the blob 1, 6. So we have about 6 tests for the non-numeric and 1 for the numeric that come from this. So about 7 tests added for the what I call the input classes, the I classes. This is based on how the data gets into X. So in our case, in this application, it's typed in by a user. So there's a lot of variety of what a user can type in. And then we look at the M class and we sort of suggest, okay, M is about memory, how things are stored and processed in memory. In this case, we might want to look at the code. We might want to talk to the programmer or the technical team working on the software, maybe the architect, and we might ask them, all right, can you give us some guidance? Can you help us to identify the type of variable something is stored in? And maybe that X is stored in a variable that is a floating point variable that uses 32 bits to store it. And there's a range of valid values. So it can go to some minimum value and some maximum value. And therefore, the classes that would be interesting to test around a variable that's stored in memory would be something that's too big to fit in the type, too small to fit in the type, or just right to fit in the type. And every type of variable used in computations in programming languages does have restrictions as to what the sort of the maximum and minimum values that can be stored in there or represented in there. If it's a 32-bit integer, for example, it goes from negative 3.4 to positive 3.4 billion or something like that. If it's a 16-bit integer, it goes from negative to positive 32,000. If it's an 8-bit integer, negative to positive 255. This is basically ranges of value depending on the type. So to learn about that, you've got to talk to the programmers about what is the type of the variable, but then you've also got to take a look at the program language binding to find out what the ranges are, and that might also be hardware, software, system dependent too. So it's important to look that up and reference the actual technology that you're using. Nonetheless, for M classes, we almost always have an M class. Somewhere, this value X is stored in memory, and whatever method is used to store it will dictate what's too big, too small, or just right. Now, how many tests do we need to add? Well, actually, all of the A classes we tested were in range for M, so we don't have to test those again. But it's probably a good idea to test something that's too large to fit in memory and something that's too small to fit in memory to see if it gives appropriate error conditions or accidentally creates false computations. So this is an equivalence analysis of X in the square root function, assuming you have knowledge of the application logic, input method, and memory. Sometimes you only have knowledge of one of these things, mostly hopefully the application logic. But you can imagine at different times in your project, you might have access to different information. So the depth of testing of X or the types of classes of testing might vary. If you're doing unit testing with the programmer while they're writing the code, you have a lot of information about the M classes and the A classes, but you may not have the I classes because the user interface hasn't been implemented yet. When you're doing system testing, you may not have direct access to the programmers, but you certainly have access to the I classes and the A classes. So at different times in different parts of the project, we may take that same variable and exercise different classes in it. If you take a look at different types of variables, they end up with different types of partitioning. So many systems have date fields that are maintained. Certainly in transactional systems, we track date an awful lot. So the date field is something we can look at. This is taken from an insurance application I worked with, and it's looking at some of the partitioning around the date field. Now we don't have, in this case, any what I call M classes. So we're not looking at how the data is stored in memory. And the first thing they'll do is they'll partition it and sort of say, okay, well, what are the classes based on the business logic? And in an insurance application, they might look at the data and say, okay, well, always a date fits into at least 3 classes. And those can be partitioned as to the present, the past, and the future. The present, past, and future. And if it's the past, is it the recent past, some sort of midterm past, long ago, or very long ago, ancient history, right? Before digital computing. And if it's in the future, is it the near future, distant future, or very far into the future? So those are different classes we can look at. Depends what the computation is, but this is basically time. So a date field can be partitioned in terms of the timeline, right? Past, present, and future. Did this transaction happen yet? It happened yesterday. It's in the process of happening. It's finished. It's not finished. Those are things related to where we are in time. And then there's other date field things related to what people would call the I classes or input classes, which would be the way that they're entered. And date fields are notorious for having many formats. And some of the formats actually look the same, but are different. So they're what we call confusable formats. Like, for example, YYMMDD is very similar to DDYYMM. It's a bunch of 2-digit things. It's possible to have confusion about these things. So when we look at the syntax here, we say, okay, well, what are the valid syntaxes and what are the invalid syntaxes? And we have to take a look at the design documentation, perhaps, to learn what they're supposed to be. And if there's an ambiguous date format, like a two-digit year, then we might want to say, okay, well, if the year is represented with 2 digits and it says 20-12-01, well, is that December 1st, 1920, December 1st, 2020, December 1st, 1820, December 1st, 2120? We don't know. So we have to be very careful about ambiguity in the dates and maybe try different things around that. Depends again on how it's processed down the stream, but these are examples of different date formats. You may want to break it down. Inputting dates almost always has a syntax to it, and then testing valid and invalid syntaxes are important. Applications try to get fancy sometimes and have all sorts of cool data input methods for dates. Once you get down to typing in strings, though, it gets very confusing. And there's no real universal standard on this. I know that people say, well, in Canada, do we always put day, month, year? And I say, well, I wish we did, but we don't always. And I've tended also, since I got into computing a long time ago, I really prefer to use 4-digit dates. I can't imagine using 2-digit dates. It's too confusing. But I'm worried, what are we going to do when 5-digit dates come around? So think about the computing in the year 10,000. What's going to happen back then or in the future then? Now, here's another example of an equivalence partition for an insurance application. So this is basically a claim amount. So the insurance application is processed on many systems. So the claim amount is just a dollar amount of a claim. And this is a generic analysis. It's very deep analysis on the input side. but it's just looking at business rules for application logic. Almost always for a claim amount, there are ranges. So there's some minimum range, some maximum range, and valid ranges in between. So the application logic breaks down into ranges. The claim amount, M classes, depend on the processing. And because this is a distributed environment with networks of many, many computers using many, many programs with many, many programming languages, we basically want to say, okay, well, maybe that we should look at M classes as all sorts of different codings. Like maybe the claim amount could be coded in 8-bit, 16-bit, 32-bit, 64-bit, or with what's called BCD coding. And whatever this is, we may want to try at least one test case for each of these to make sure that, for example, a value that's too big for a 16-bit one still gets processed correctly. So this, again, you're looking at multi-processing. There's transactions going all over the place. There's going to be many technologies, so you might have many M classes for the same variable that are interesting to test. In terms of the syntax, we break down to valid and invalid syntax. Invalid syntax, there's a lot of stuff in here, like for example, alphabetic characters, strings that are too long for the input field, control characters, what are called literal strings. For example, if someone types in a lowercase l or an I or a 1 or a vertical bar meaning the same character. And that's people who learn touch typing on ancient manual typewriters would actually make that type of mistake because they didn't have a separate key for uppercase I, for example, and lowercase l and the digit 1. There would be one key for all three. So that's called literal strings. SQL injections, those are hacks. Broken HTML is always interesting to try to put into an input field. So you have tons and tons of analysis on invalid syntax, some of which are numbers that are not in supported syntax. And then we have the valid syntax. And in this case, there was a particular interest in numbers coded with or without leading spaces. So if the number's got leading or trailing spaces, it's still for them syntactically valid. So they have to truncate the spaces before they process the values. So that's just based on what is the input mechanism here in the insurance application for the claim amount. AIM. A lot of different ways to look at it. Sometimes you have variables that are used in all sorts of interesting processing. So we took a look at Gmail, and I don't know if you remember in the section we did on variable identification, we looked at sending a mail with an image attachment and tons of variables that come up. Well, this is a breakdown of one of those variables using equivalence partitioning. The variable in question is to composed. So in terms of composed, what we mean is when we create an email, it's not the received mail, it's the composed one. So the to, who is the mail going to? We have documentation requirements that help guide us. So we have like, what does the user interface look like? We have API description of the to field that's published by Google. And we also have source information about the variable types in Java, for example. And these are explicit references that we pulled out. So this is like our requirement information, the information we have that's going to help guide us a bit in identifying the classes. The to field, we have, of course, classes broken down based on application logic, input methods, and memory classes. And at the time, we were looking at how definitely are things processed by Gmail. And so they cared a lot about the assignment and redirection of email addresses and stuff like that. For input, we looked at what someone can type in, what can enter. And for memory classes, we looked at how things are stored and processed in memory. So just breaking them down, for the A classes, this is for to composed in Gmail. Well, an address is broken down into a name at domain. For example, the domain is gmail.com, the name is robsab. So for application logic, then we're going to start with the domain. And we say, well, is it a real domain? So is the domain assigned? Has the domain ever been assigned but not assigned now? So previously assigned, this happens a lot. And never assigned. So you have domain assigned, previously assigned, never assigned. If it was assigned, has the name been assigned? So is it a valid email address? RobSab, has it been assigned? Name assigned, previous assigned, or never assigned? And for the case of a name that's assigned and a domain that's assigned, is it redirected or not? And is it in a contact list or not? And this is the processing of Gmail to take care of the address to basically send it on to the world email system. It's going to do a little bit of application logic in there, sort of help routing the mail through the Google universe. Now, these are A classes. So you can imagine here, you'd have to choose several interesting values to test this. But it makes sense if this is how the business logic treats addresses. It's not just a syntax thing, it's about the business logic of the email. So the thing about, like, is it redirected or not, in a contact list or not, affects how it's being processed by Gmail. So those are A classes. Now, the A class also might be just trivial, saying exists or not. That might be enough. It depends what your application does with email. Input classes for syntax. There's a lot of interesting ways to analyze syntax of emails. Indeed, you can create syntax diagrams and look for things that violate the syntax diagrams if you want. I just broke it down here in terms of a simple mind map, saying, well, one is a valid syntax. So whatever that is, there's valid. And one is invalid syntax. And invalid, well, we have the possibility of a valid domain, but an invalid name, or an invalid domain, but a valid name, and an invalid name with an invalid domain. So you have those three possibilities. Then there's the actual technical aspects. No at, for example, the string is too long in aggregate. There's text characters that are not allowed in email addresses. There's control characters that are not allowed in email addresses. There's binary objects that are not allowed in email addresses. The string is way too long. Maybe it includes non-ASCII characters, which might be similar to control characters. And you can make this list longer if you want to break it down. Certainly, people who study security would tell me that we should also be looking for things like SQL or HTML hacks in email addresses. Okay, so that's input methods, how the data got there. Memory classes, well, if you look at the actual API definitions, it's just a string. It's just a string. And a string can be as large as 2 to the 32 minus 1 characters in Java, at least for the Java string type that Gmail uses. This is a ridiculously large number. Probably it will be blocked by something else that is an input method thing that's going to block us before we get anywhere near that side. I couldn't find any information about that. I'm sure that the user interface has a minimum value and not a minimum, but a maximum value length that I didn't identify. So this is just based on the C programming language. It would be interesting to try to call an API with a string that's larger than that, but I don't think that's even possible. So that might be then a moot point. We don't have to test something that's impossible to test. Still interesting analysis. Now, the last thing I want to suggest about equivalence classes is that some equivalence classes have ranges of values. For example, there's numeric ranges of values and there's strings that have different lengths. So it's considered a useful thing to exercise equivalence classes which have ranges of values on the boundaries. Now, once I've got an equivalence class with a range of values, I like to identify boundary tests for it. So this is over and above my tests of the class. I want to find boundary tests of it. And there's two strategies that some people use for this. One is called 2-point boundary testing, and one is called 3-point boundary testing. So in 2-point boundary testing, what we want to do is we want to identify the minimum value of the range and then test exactly the minimum and just below the minimum. And then we test the maximum value of the range right on the maximum and just above the maximum. So if there's a number that's supposed to be between 10 and 1,000, and it's supposed to be a whole number, an integer between 10 and 1,000, well, the minimum will be 10. So the tests we would do is we test at 10, we test just below 10 would be 9, then we test at 1,000, we test one just above it at 1,001. So that would be the min, just below the min, the max, just above the max. And that's a 2-point boundary analysis. And those tests are very interesting tests. Boundary bugs are common, pervasive. They're all over the place, and they keep coming at us in software engineering. So exercising 2-point boundaries helps to ferret out boundary bugs. There's also some people who prefer to test what's called 3-point boundary tests. Actually, when I first learned from practitioners about boundary testing, I was encouraged to use 3-point boundary testing. In a 3-point boundary test, what you do is you identify that range. So if the range is between 10 and 1,000, so you start with the minimum, you test the min, just below the min, and just above the min, and then the max, just below the max, just above the max. So from 10 to 1,000, the min would be right on the min is 10, just below is 9, just above is 11. So I test 9, 10, 11, and then for the max, I would test right on the max, which is 1,000, just below, which is 999, just above, which is 1,001. Now you got to keep in mind that the one that's just below the min or the one that's just above the max, those are out of the class, right? So they're out of the class. They might be in another class, but they're still interesting to test because you want to make sure that the boundary is not confused. So your expected results should be in a different class than the one that you're actually looking at to identify the test case. So that's 2-point boundary testing and 3-point boundary testing. Anyhow, that's where I'm going to stop at this point, talking about equivalence partitioning.